Hi, everybody. Let's finish up chapter 15. We're going to do chapter 15, section 5, triple integrals in rectangular coordinates. Remember, integrals are used to find originally areas under a curve. Triple integrals are used to find the volume of a three-dimensional shape in space. That's one thing. Another one we could use it for is to find the average value over of a function f(x, y, z). That's me. Over a three-dimensional region. And chapter 16 will discuss more complex uses of triple integrals. We're looking at vector fluids, vector fields, fluid dynamics, all this stuff. So we're going to see how things move across the surface of an object. Triple integrals. If f(x), y, z is a function defined on a closed and bounded region of D in 3D space, the integral of our function over that region can be defined as, this is going to show us how we do it. Partitioning rectangular box-like, okay, we'll draw pictures of this, rectangular box-like regions that contain the parts of the region we're talking about into rectangular, we call them cells. By planes parallel to the coordinate axis. Denote axes. What that means is here we have our X, Y, and Z. So if we define, let's say, an object, a rectangle here, the x components, the ones that intersect the x-axis, are parallel to the yz axis. The depth, so we'll call these delta x. No, that call this delta y. Those are perpendicular to the xz plane. The delta x, the ones that goes this way, are perpendicular to the yz plane, but parallel to the x-axis. And then the vertical ones are perpendicular to the xy plane, but parallel to the z-axis. Okay, so that's what we're going to do first. We have some shape height here in 3-dimensional space. We first partition those, then we numbering the cells that are completely inside our object, our space, from 1 to n. In other words, if we have part of the space that looks like this, and we have a box that looks like this, we can't use it because it's part of that box is outside that shape. The kth such cell, the kth cell, has the dimensions delta x sub k. That's the width, the x-axis, by delta y sub k, the horizontal, by delta z sub k. Remember, it's a cube, so it's going to have 3 dimensions. Where the volume will be defined as the change of the volume, because it changes however many more x's we have, those deltas we have. We multiply each one of those. All right, then our last step is choosing a point x sub k, y sub k, z sub k inside each cell. That will give us the sum Sn. This is summation for k equals 1 to n of our function at each of those points times our delta v. When we add up all that, then we'll have the total volume of the whole object. So with respect to these delta v's, delta x, and delta z's, our goal is to partition our object D into smaller and smaller cells. In other words, as our delta x's go to 0, our delta y's go to 0, and our delta z's go to 0. As all those go to 0, we use the norm and it goes to 0. Remember last section that the smaller they get, the more terms we have, and so eventually the number of items, goes to infinity. Yeah. So I should have set there. As our norm goes to 0, the number of cells n goes to infinity, and the sum of all our boxes or volume areas becomes some limit. And that limit is what we're looking for. It's called the triple integral of our function over D. So this, remember, so we're saying as our n's go to infinity, the sum of all those become our triple integral over D of our function times our volume, the dV. We're integrating it with respect to our volume. So this actually relates to our norm aspect. The limit as our norm goes to 0, it becomes our triple integral of dx, dy, dz. Again, remember, and the order of integration is not important, but in this chapter, this is where it's going to be more important to figure out, learn how to change the bounds of integration. The volume of a region in space. If our function f x, y, z is a constant function, f x, y, z equals 1, then the sums become summation of k's from 1 to n of our function xk, yk, ck. So if our function is 1, delta p sub k, then our sum becomes delta v sub k. Basically what that says is the sum of all of our little boxes, we add them all up, and that gives us the volume of our object in three-dimensional space. As our x, y, and z parts, the change of those, the volume, the size of those get very small. The cells of our function eventually get smaller and smaller, smaller. And then they define a more accurate description of our object. So what that means is our limit, how it relates to what we just talked about there, the limit of our S sub n as n goes to infinity, and as we stop here, the S of n becomes this. So as the limit of S of n equals the limit of our function, that can be now defined as our triple integral with respect to dv. And a lot of our examples and our assignments we'll take it as just this. Because here, if you notice, there's no function. That's because we're taking this stage as our function is equal to 1. And that way you could also give you free reign of choosing whatever bounds of integration you want to choose. Let's define volume. The volume of a closed bounded region in D of D in space is defined as the volume equals the triple integral dv. That, whenever we're asked to find volume, will now, where dv is dx, dy, dz, in any order we choose. Finding limits of integration in the order dz, dy, dx. we use Fubini's theorem to evaluate triple integrals. By repeating single integrations. Evaluate our function. So what that means is each one of these integrals are taken as their own piece of the puzzle. So what really happens is you're actually taking a single derivative. When you do that, then you do the other one, the next one. So each one of those are their own processes. And as we go along, we build up the variables used. And the last integral is going to be the bounds set of what our value is going to be, because we have to go away from the variables and get a solid number, an integer. Okay, so as our statement of top set we're doing dz, dy, dx. So what this says, we first integrate with respect to z, because we read this way, left to right. Next, we integrate with respect to the next one, y. And lastly, we integrate with respect to x. Yeah, yes. Even though the order of integration doesn't matter, we read inside out. So there's the first bounds of integration are the z's, the next one is the y's, and the last one is the x. So as we define these bounds, we have to define the bounds of, in this case, z first, then y, and then what are the bounds of x. Here are the steps. Steps of triple integrals. As always, whenever you can, always sketch the region D. Along with its shadow, R. The shadow is the vertical projection of the shape onto the region of the last two variables. So since we have dz, dy, dx, on the XY plane, that's where we're going to project our shadow. If it was XZ, then we project our shadow there. All right. So once you draw your graph, label the upper and lower bounded surfaces of our shape. Then label the upper and lower bounded curves of our shadow. Now, what does this mean? Here's our X. Here's our Y. And there's our Z. So let's pretend we have, I'll make a circle, a sphere. It's up here in the, let's say, in the first octant. So since we're doing dz, dy, dx, we project down on the xy the shadow of the sphere. So here, the upper and lower bounds, we have our upper lower bounds. So we have z1, z2. That's function 1, function 2. All right. Now the bounds going down, since our last the last bound of integration is the x, we find our this is our region R, this is a region D. All right, so this will be defining the integral range, the bounds A and B. These are defined as our Y values. This is Y1, this is Y2, and that's some other function. So notice in the original object we had, it's a 3 dimensions. We have x, y equals z. On this one, it's only 2 dimensions. We have the object here is now defined by a single variable. So we have to find the formula for z, upper and lower bounds. Then we have to find the formula for y, since it's the middle one. And then the bounds of x, since the last one, are where the shadow begin and end. Now, this is where how we define and calculate our bounds of integration. Finding the limits of integration for z. draw a line, we call it M. From a point XY in our shadow. That is parallel to the Z-axis. So we pick a point in R. Doesn't matter where that point is. That point is X, Y. Since Z is our first bound of integration, we draw a vertical line. That's M. It's parallel to the Z-axis. All right. Now, we're now defining these. Now, the lower bound is this line we have here, this vertical line. Where it first touches the graph, the D, the object we're looking at, that's our lower bound. So that's where it first touches our object. And then as it goes through, where it exits that graph, that's our second bound. So that defines our upper lower bounds of integrations for our first variable. All right, now let's look at what happens for the next variable. To number 3. Let me finish writing this out. Draw a line M from a point R that is parallel to the axis. The point where M enters our object in 3-dimensional space is the lower bound. Where M exits our graph upper. That's Z2. All right. Now let's find the next bounded region of integration. Get my dog quiet. Sorry about that. So finding the next bounded region of integration, this is Y. Now, since, remember, our integration order goes this way. So again, to recap, to find DZ, pick a point in R, make a vertical line parallel to the Z-axis. So now we take a point in XY parallel to this one. Now, for the y, we'll take a line that's parallel to the y-axis starting from x. This is our region R, and it matches that sphere up on top we had. So now for the y, we have our bounds of A and B. Now for this one, we're going to pick a point in R. Actually, it'd be easiest if we pick the center, if we could. That one's supposed to be perpendicular. Yeah. So since X is the last one, we draw a line perpendicular to X going through R. We call that line L. So because L has to be L from the X axis, that is parallel to the Y axis, going through R. So where it first enters R, the lower bound is where L first enters R. So the lower bound is R, G1 of X. That's Y1. And our upper bound is where L exits R. So this point here, that's Y2. So upper bound is where it exits. So as L, this is L moving forward, our Y2 is G2 of X. So the bounds here, Y1 is, that's where it enters, Y2, and that's where it exits. Right. Finding the last integration factor. In this case, it's going to be dx because it's the last one. We're going to find the upper and lower bounds there. The upper and lower bounds for the last one are the points that are perpendicular to the L. It's the axis perpendicular to X, the axis, where the graph the shadow first begins and the shadow ends. So the lower bound is equal to A. And the upper bound is equal to B. Remember, the last bound's always a number. And then we have our two other ones. So this is what this is what it's going to look like when everything is said and done. So our triple integral becomes this. We have x equals A, x equals B, y equals g1 of x, y equals g2 of x, z1 is f of xy, and z2 is fxy there of our function. Since we have z here, then y, then x. So the innermost bound has to include the other two remaining variables. Because what we're doing is, as we're going out, as we're doing each of these integrations, this is integration 1, integration 2, integration 3. All the z's will be gone. It will be replaced by x and y's. After the second, we'll have only x's. So then when we plug in, do the third one, all the x's are defined by numbers, and we get a solid answer. And remember, the shadow is defined by the last two bounds of integration, the variables. So these two define your shadow region. So if everything works right, this procedure works when, one, we have a solid region D that is bounded above and below by some surface, and the shadow region R is bounded with an upper and lower bounds of the curve. Right, let's look at some examples here. Where are my example sheets? Yeah. Here's the first one. There. All right, let S be the sphere of radius 5, centered at the origin, and let D be the region under the sphere that lies above the plane Z equals 3. Set up the limits of integration for evaluation of the triple integral of a function f x, y, z over the region D. So it's a sphere, which means we use that formula. The radius is 5, which is and we also know that C equals 3. So let's draw what we have so far. The radius is 5. So it's a sphere of radius 5. That's on the x, but we want it to be up here. We want to be 3 units above. It's a sphere. That's supposed to be round. Now we want it to be, so this is also 5. The highest point here has to be 5. All right, so we want to, at 1, 2, 3, we wanted to have that's where we want to start. We want to start our calculations from there, under the curve there. So what's going to be that radius? This is going to be 3. So if we're looking at it, 1, 2, 3, we have 4, 5, 1, 2, 3, 4, 5. We have a sphere. But we only want to start it from here. Region of the sphere lies above the plane z equals 3. So we want, that is what we're looking for. So our formula for that one is, there's z. So it's going to be square root of 25 minus x squared minus y squared. So our bounds of integration, we're going to do dz first. So that means we'll have dy dx afterwards. So from here, we could put down our shadow. So this is R. This big old thing here, up here is D. So our shadow will be in here. Okay. Well, no, not this is 3 here, not 3. So this, we don't know what this is yet. But we can figure it out. We have x squared plus y squared plus c squared equals r squared. We're saying z is 3. And r is 5. So x squared plus y squared is 16. So this is centered. So our radius here is 4. Because z is equal to 3. So if we drew the graph, how wide is it? It's from -4 to 4. Because our circle centered is at the origin. 16 is r squared. Okay, so now that's what we have our shape. Now we can figure out what our bounds of integration are going to be. So the volume is triple integrals of our function dz, dy, dx. So our z function, which we figured out earlier, z is this. Where if we drew a line from R straight up, parallel to the z-axis, this is our M. This is our M. Where does it touch the curve? It first touches the curve. Here's our shadow. If we drew a vertical line, this is, see, it first touches the curve at 3. And then it exits at this equation. (25 minus x squared minus y squared). So those are the bounds of integration of our z. Now, to figure out our bounds of integration of y, since x is our last bound of integration, we know our x is going to be from -4 to 4. We know this one already, because that's where the curve begins and ends. So what we have to look for now are these, using this formula. Solving for y, that's what we're looking for. So we solve y squared equals 16 minus x squared. Square root both sides. So y equals plus or minus 16, square root minus 16 x squared. So the lower bound will be -16 minus x squared, and the upper is 16 minus x squared. So again, on the z, we have x and y. So that takes care of that one. Now on the y, all we have left is x. We only have a function with respect to x, or a number. And then x are the bounds of integration. And then we'll take it from there and find the integral of that. That's circuit number 2. Set up the limits of integration for evaluating a triple integral of the function f over the tetrahedron D. Let's first draw a graph. X, Y, C. So we have a point at 0, 0, 0. We have a point at 1, 1, which is here. We have a point at 0, 1, 0. So it's another point there. And then we have another point at 0, doesn't go anywhere, over and then up 1. So this is our shape. We have to integrate with respect to that now. We're going to go dz, dy, dx. That's what we're going to do. All right, so what do we have here? What is our z? The z-up is made of the points. So it starts off at 0. When x is 0, y is 1. When x is 1, y is 1. And there's no x. So the function we're going to have here the shadow is on the xy already, so going up, it touches the curve at that one. So it touches the curve on the lower bound is 0. And it would just exit in this slanted field there. And that field is y minus x. 1 minus 1 is 0. 1 minus 0. There's an anomaly. So the top bound would be where it exits. Z is equal to y minus x. Yeah, because it has to be that way because z plus x equals y. If x is 0 and y is 1, then z is 1 because it's on the back. Yeah, so z is equal to y minus x. So now let's look at our other formula. Here is our domain. Since maybe this is our m. Now, since our x is the last one, we have to draw our L. Where it touches this curve, this line here, which is y equals x. Because if you just look down on the xy, we had 1, 1, 1. So that's the line y equals x. So it first touches it when y equals x. And it exits on the very last point of y, which is 1. Oops. It enters at y equals x and exits at y equals 1. If you look at it this way, our graph really looks like this from on top. So perpendicular from X, I'm touching the graph y equals X, which is the lower bound, and it exits when y equals 1. And where does X go? X goes from 0 to 1. So our bounds of integration are 0 to 1, X to 1, 0 to y minus X. Again, it changes if we rewrite these a different way, then our graph changes, then our order of integration changes, and our equations change. Let's look at another example. Find the volume of the tetrahedron from example 2. So we're using the same graph. There's a point at 1, point at 0. So it's flat on the xy plane. Find the volume of the tetrahedron where f equals 1 over the region. So now we have to actually integrate it. dz, dy, dx. All right, since it equals 1, let's do the first integration. The integral of 1 is y. So that's 0 to y minus x. Zero to 1, x to 1. So it's y minus x minus 0 dy dx. Next, we got to do with respect to y. So the integral of y with respect to y is y squared over 2. The integral of x is xy. So in the first one, we have 1 squared over 2 minus x times 1 minus x squared over 2 minus x times x. Minus x squared over 2 minus x squared, or negative makes it a plus. Distribute that negative. So 1/2, negative 1/2 plus 1, it becomes positive x squared over 2. So our last integral will be with respect to 1/2 minus x plus x squared over 2. Now, it's easier if we have fractions to get rid of the fractions and just deal with the numbers, and we'll put the fractions at the end. So if we factor out a 1/2 from everybody, this one is over 1, so we have to make it 2/2, which now leaves us with 1 minus 2x plus x squared. See, it's be much easier to do that. And then we just multiply by 1/2 at the end. The integral of 1 with respect to x is x minus 2x squared over 2 minus x cubed over 3 from 0 to 1. We don't have to worry about 0, so all 0 should be 0. So all we do is 1. 1 minus 2's cancel. 1 squared minus 1 cubed over 3. One minus 1 minus 1/3. That's a plus. It's a plus. 1 minus 1 cancels. So we have 1/2 times 1/3 equals 1/6. And that's our volume. Now I said, then do the same calculations using the other. Okay, now we have to do the other order of integration. Part B. So now it wants us to do the same thing, but now with dy, dz, dx, using the same graph. There's a point at 1, 1, at 0, at 1, and at 1. So it's on the XY graph already. That's the last one. So our bound is going to be from 0 to 1 on the very last one. Now, since we're doing dy first, our shadow is on the XY plane. So the shadow, if we draw a perpendicular line to it, so it's on the ZX, which here, it looks like this. We want to be parallel. Our M has to be parallel to the y-axis. Remember, our equation we had was z plus x equals y. So going this way, when we first touch the graph, it's at z plus x, and it exits when y is 1. All right, now we have to draw another bound of integration, a line. That's from the x-axis into the shadow. So this is our L line. So it starts off at 0, and it goes to the line here. Now we forget what that line is, the equation of that diagonal line. Well, we know that. So we have z plus x equals 1. On the z-axis, we have 1 minus x. That's where it leaves. We're doing it with dy, dz, dx. And our function is 1. So with respect to y first, so the function here, integral is y from z plus x to 1 dz dx. Okay, so the first one is 1 minus c plus x dz dx. 1 minus that. From 0 to 1, 0 to 1 minus x. Our function is that dz dx. Now we integrate it with respect to z. The integral of 1 is z minus c squared over 2 minus xz from 0 to 1 minus x dx. Since they all have z, we have to worry about this one. So we get 1 minus x minus 1 minus x squared over 2 minus x 1 minus x. Dx. So I put this anywhere a place I see is z. One minus x. 1 minus x squared becomes 1 squared minus 2x plus x squared over 2 minus x plus x squared dx. One minus x minus 1 over 2 minus 2x over 2. No, that's plus. That's a minus 1 squared over 2 minus x plus x squared. Choose cancel, so positive x, negative x cancel. So this is 1 squared. Negative 1 squared is 1. So the 1's cancel. All we're left with is x plus x squared. dx. So integrate that with respect to x. We get negative x squared over 2 plus x cubed over 3. Doesn't matter for 0 because they're all zeros to cancel. So we get negative 1 over 2 plus 1 over 3. Get a common denominator. One over 6. That's 3 over 6 negative. It can't be negative. I'm messing up a sign somewhere. Okay, I have a sign issue here. It becomes negative 1 over 2, positive 2 over 2x. Or, oops. Negative x squared, not 1 squared, x squared over 2. Let me start from this point over. So we have from 0 to 1 of 1 minus x minus 1 minus 2x plus x squared over 2. So it's 1 minus x minus 1/2 plus 2x over 2 minus x squared over 2. That cancels. So we have 1 minus 1/2 is 1/2. X plus x, these cancel, so we have minus x, negative 1/2, so it makes it a positive 1/2 x squared. Now we factor out the 1/2. We have 1, 2x, because we have to make it 2 over 2, plus x squared. One half integrated, it's x minus 2x squared over 2, x cubed over 3 from 0 to 1. Since they all have x's and zeros at the bottom, we have to worry about that one. So x is 1, 2 over 2 cancel. One squared is 1. 1 cubed is 1. Those cancel, so we have 1/2 times 1/3 equals 1/6. Yeah, that's what we're supposed to have. All right, let's look at another example. Where's my example sheets? Let me look for them. Example 4. Find the volume of the region enclosed by the surfaces Z and Z. We're going to use the triple integral dz dy dx. Okay, first, what's that one going to look like? That's an oval one. And that's the blob above it. X, Y, Z. So this one, when X is 0, let's look at this one first, though. It's got one Z is 0 at the origin. So we have 8 equals X squared plus Y squared. Yeah, this, okay, so with respect to Z, well, we know that both Z's have to be equal. Let's look at the bounds or the limitations of here. So we have X squared, 3Y squared. Just going to see whether Z is above or below. Okay, so move the X over here, move the Y over here. So we have 2x squared plus 5y squared equals 8. Divide everybody by 2. X squared plus 2y squared equals 4. So now this gives us a better picture of our oval. This one's going to be, so R equals 2. So when 1, 2, 1, 2, so we know it goes there and there. So when X is 0, Y is square root of 2. It's a little bit smaller. So it's an oval, football type thing. So that means our graph is up here and they're all parabolic in shape, paraboloids. So pick a point anywhere in our graph, draw a vertical line that defines our M. dz, dy, dx. Now looking at these two equations, which one's smaller? Because they both equal z. Let's see, so when x at the origin, let's see. When x is 0, y equals 0, this one's 8. So this is the taller, this is the lesser. So for my z's, I have x squared plus 3y squared, 8 minus x squared minus y squared. Next, I gotta look at with respect to y. We could use this one. So we have x squared plus 2y squared equals 4. Subtract x squared from both sides. Divide by 2. So y squared 4 minus x squared over 2. And square root both sides. Plus or minus 4 minus x squared over 2. So those are the bounds of our y variable. The second one, negative 4 minus x squared over 2, positive 4 minus x squared over 2. And now for our x, since the radius is radius, no, I don't say radius, but the longer form of it is from negative 2 to 2. Because when we square root both sides, it's positive negative, so it's negative 2 to 2. Okay, now this one's not going to look fun, simply because it has a lot of variables here. We first take it with respect to z. X squared. So this is z, and it's from 8 minus x squared minus y squared to x squared plus 3y squared dy dx. So this one's going to be this minus this. So that becomes minus x squared minus 3y squared, 8 minus 2x squared minus 4y squared. Okay. So it's from negative 2 to 2, negative 4 minus x squared over 2 radical, to positive 4 minus x squared radical 2 of 8 minus 2x squared minus 4y squared dy dx. The integral of 8 is, with respect to y, is 8y. Of y squared is, or x squared y, 4 y cubed over 3. Okay, actually, we can make it. We have to eventually multiply it anyway. Well, let's see this. So we'll start with this one. 8 times radical 4 minus square 2 minus 2x squared 4 minus x squared over 2 minus 4 times radical 4 minus x squared over 2 cubed minus 8 times, let's be negative 8 radical 4 minus x squared over 2. Change that sign to plus 2x squared radical x squared over 2. I'm changing it because this will change all the signs. So this negative goes through and changes all these signs. So it's going to be 8 4 minus x squared over 2 2x squared negative negative makes it a plus. Negative makes it a minus 2x squared. Makes it a minus. Now everything just doubles. So 8 plus 8 16 negative 2x makes it negative 4x squared. Then 4 over 3 plus 4 over 3 is 8 over 3. Wow, it's going to be a lot of writing. Can we simplify this? This is going to be its own equation. will be 16 minus 4x squared times that. Okay, so now this becomes 16 minus 4x squared. Let me write this real quick. All right, so here we can factor out a 4. That makes it 4 minus x squared. I divide by 2 here, I'll multiply by 2 out here. Now what we have is this one is actually 2 over 2, because this one's 1 over 2 with that radical. This is 3 over 2, so we have to get the same. So we could do that. 4 minus x squared over 2. 2 over 2 plus 1 over 2 is 3 over 2. 4 minus x squared over 2. 3 over radical 2. Now this can become 8. We combine these two. 8, so it's 24 over 3. 16 over 3. 4 minus x squared over 2. I combine these two. Just the coefficients. That's let's see what this one becomes. So we can split these up. This one's going to get ugly really quick. But we only want with respect to x, so we can separate those. So now this comes out in front. So this one becomes 2 radical 2. Multiply top and bottom by radical 2. So this becomes 2 times 2, makes it 4. 4 goes into 16 4 times. Now I have to look at the properties for integral. Sorry about that. My earphones died. I have to recharge them. All right. So we left up here. After everything is said and done, we ended up with 4 pi square root of 2 with that. Now we have to integrate this function. That's where it gets complicated. To integrate from -2 to 2, we have to use the identities. We're going to be using trig identities as well as an identity for integration. First off, let's review the trig identities that we'll be using. Sine squared plus cosine squared equals 1. The double angle of sine is equal to 2 sine x cosine x. So the 4 angle of sine is 2 sine 2x cosine 2x. The double angle of cosine is cosine squared x minus sine squared x. Cosine squared x is equal to 1/2 1 plus the double angle of cosine and cosine squared 2x is equal to 1/2 1 plus cosine 4x. All right, so those are the identities we're going to need. First off, let's define x as sine u, or in this case, 2 sine u. So let's keep it. So the derivative of that would be cosine u du. So what we have right now is this. I'm going to leave this off right now, put it back at the end. And I'm not worried about this just yet. So we have 4 minus sine squared u to the power 3/2 du. Right. Cosine u du. Now it's got to be 2. Because we have to have 2 there, so that becomes, it actually becomes 4. So because if we square it, we square sine u of x squared, so that's squared, so it's 4 sine u. So x is going to be 2 sine u. All right. So what we can do first is we can factor out the 4. This is all still 3/2. 2 cosine u du. Now we can split these up into 2 separate equations. So here we have 4, the square root of 4 is 2. 2 cubed is 8 times 2 is 16. Cosine u d. So again, it's 4 to the 3/2 power is 4 to the power 1/2 cubed. So square root of 4. 2 cubed is 8 times that 2 is 16. All right, so 1 minus, so we have sine squared plus cosine squared equals 1. So cosine squared is 1 minus sine squared. So this can be written as cosine squared u so the square and that square cancel, the half and square cancel. So we're left with 16 cosine cubed times cosine u du, which makes it 16 cosine to the 4th u du. Cosine these two multiplied. Right. We don't have a rule for this one, but we do have for cosine squared. So what we actually bring the 16 since it's a constant, bring it out in front. So we have cosine squared u squared du. Looking at our properties, cosine u is that equation. Cosine squared is 1/2 1 plus cosine 2x. So it's 1 plus cosine 2u squared du. So here we're using rule 5. Now we have to expand this. Becomes 1 plus cosine 2u times 1 plus cosine 2u is 1 plus 2 cosine 2u plus cosine squared 2u du. Got the 1/2. Got the 1/2 here. So when I square that, becomes 1/4. And the 4 and the 16 cancel, giving us 4. Plus 2 cosine 2u plus cosine squared 2u du. Yes. Let's take each one of them separately. So it's going to be cosine 1, 1 integral of 1 du, 2 cosine 2u du, cosine squared 2u du. So 1 u cosine 2u du, cosine squared 2 double angle. I can use rule 6 and rewrite it. Is 1/2 1 plus cosine 4u du. All right. We're okay. The integral of 1 is u. The integral of let's see, integral. Oh, no, we need that to keep that there. We need to keep that 2 inside there because the derivative of the integral of cosine 2u is it's going to be sine 2u because we have to have that 2 in front. So it's sine 2u. Derivative of sine 2u is 2 cosine. We have integral of 1/2 plus, I'm distributing these two. Integral of 1/2 cosine 4 du So in order to do this integral, I need to have a 4 in front, so I have to divide by 4 in front. Or u plus sine 2u is 1/2 u plus 1/8. The integral of that is sine 4u. If we get everything in the same denominator, we take out the 1/8. So this has to be 8/8, 8/8, or make that 8. So we take out the 8, leaving us with 8u plus 8 sine 2u plus 4u plus sine 4u. Eight plus 4 is 12u. 8 sine 2u plus sine 4u. Sine 2u sine 2u is 2 sine u cosine u. And sine 4u is sine 2 goes 2 sine 2u cosine 2u. All right. So we can distribute that 1/2 everywhere. So we have 6u plus 4 times 2 sine u cosine u. The 2's cancel, so we have sine 2u cosine 2u. Not done yet. So this is 8 sine u cosine u. Multiply those two. Now sine 2u is 2 sine x. So this first one is 2 sine u cosine u. And cosine 2u is cosine squared. So this is cosine squared u minus sine squared u. I need to get it down to the single use because we have to convert it back eventually to the x's. Sine u, cosine u. Now we have to multiply this times this, this times this. So we have 2 sine u, cosine u. Actually, no, we don't. We just leave it like that. Yeah, we'll just leave this. It'll save us some time. So let's not do the distributive. So now we have to put it back in terms of x. Remember we said earlier x was 2 sine u. We have to get solve for u. So x over 2 equals sine u. So u is equal to the arc sine of x over 2. So now everywhere we see a u, we put arc sine x over 2. 6 arc sine x over 2 plus 8 sine arc sine x over 2 cosine arc sine x over 2 plus 2 sine arc sine x over 2 times cosine arc sine x over 2 times cosine squared arc sine x over 2 minus sine squared arc sine x over 2. We have 6 arc sine x over 2. Arc sine times arc sine is just x over 2, so it's 8 x over 2 which makes it 4. Actually, I think I have another one here. Yeah. They said use this. We can't. Crap. The instructions said x sine u. Let's push. Oh, it didn't tell us. Okay. So yeah, if we didn't have that, then let's make it just x. it'll make it much easier for us. It'll give us relatively the same answer, but so the cosine of arcsine is going to be the square root of 1 minus x squared. Remember, sine is x, cosine is y. So that's what I'm solving for. Plus 2 sine arcsine is x times cosine, which is 1 minus x squared. Times 2x. So this one, since it's squared, it's going to be 1 minus x squared. And that's sine, so it's squared, so that's just going to be x squared. Because cosine and arcsine is square root 1 minus x squared. If I square root, the radical's gone. Sine arcsine is x squared, makes it squared. Six arcsine of x, 8x times radical 1 minus x squared. This becomes 1 minus 2x squared. Okay, now we could take, this is our integral, so we have from -2 to 2. Yeah, this was not a fun one. So from 2, we have 6 arcsine 2 plus 8 times 2, 1 minus 4. 2 times 2 is 4. 1 minus 4. Minus 6 arcsine -2 plus 8 times -2, 1 minus 4, -4, 1 minus 4, 1 minus 8. Plus 16 minus 4. These are going to cancel. Positive, positive. They're not canceling. That should be -7. Negative makes positive. So negative. Yeah, these would be negative times negative makes it a positive. So that's going to change it back to a negative. So those cancel. Negative makes it positive. So they're going to add. They're going to subtract. So we have 6 arcsine 2. Those disappear because those are, we can't use those for negatives. We can't do those because you can't be larger than one -1. I'll do a revision of this one once I figure out what I did wrong. It's just that one just took forever and ever and ever. Yeah, we still had the 4 radical 2 over 3 times 6, whatever that equals. Which is 8 radical 2 times whatever that is. But I'll fix that. I'll find out what I did wrong. And the last thing we're going to talk about here, the average value of a function in space. The formula we'll be using is 1 over the volume of on D of D, the triple integral of the actually the volume there. So that's the formula for the average volume. And here's this example. So let's draw the picture. It's a cube. D region bounded coordinate planes. X equals 2, Y equals 2, and Z equals 2. We have to know that cube. Since X times Y times Z is the volume. We get 2 times 2 times 2, which is 8. Now, that's the first part. Now we have to figure out the volume of this cube. So we'll do, well, x times y times z, dx, dy, dz. That actually doesn't matter because they're all going to be the same sizes. The bounds of x are from 0 to 2. The bounds from y are 0 to 2, and the same for the z's. So the first step, integrate with respect to x. We get x squared over 2 yz from 0 to 2. Zero to 2. So this is going to be 2 squared is 4 over 2 yz minus 0. We do the same thing. 0 to 2. Integrate with respect to y. We get y squared over 2. From 0 to 2. Which gives us, again, the 2's cancel. So 2 squared is 4. So it's 4z minus 0. And then integrate with respect to z. We get 4z squared over 2 from 0 to 2. The 2's cancel. So we have 2 squared minus 0. And our volume is 8. So the average is 1 over 8, which we calculated up above, times this 8 equals 1. So that's the average volume of the cube. Okay, good luck. I hope there aren't any homework assignments that are like that number 4. I'll repost that one. Sorry, everybody. Good luck.